All right, this video is going to cover the Routh-Hurwitz criterion and how it relates to stability. So we've already learned how to determine stability by determining the poles of a transfer function, right? That's what we've done previously. However, what if we can't determine the poles easily? So for example, let's say we have a transfer function where its denominator is s to the fourth plus 3s cubed minus 3s squared plus s plus 1, right? We don't have a quick way to be able to determine what the roots or the poles for this are. What we could do is use numerical solvers, right? But what we also can do is use the Routh-Hurwitz or the Routh-Hurwitz criterion. So how do we use the Routh-Hurwitz criterion? We first need to build a Routh table. Then we use some established rules to determine where the poles are located on the complex plane, right? And that's going to determine our stability for our system, right? Poles in the left half plane, if they're all there, then that means that the system is stable, right? And then we could also actually use the Routh-Hurwitz criterion in a few classes for controller design or just design in general. But the question is, how do we get a Routh table in the first place, right? How do we determine stability for, say, this fourth order transfer function? So the first thing that you're going to want to do is start with a closed loop transfer function where we'll only be using the denominator. That's really the thing that we're going to be focusing on. So let's say g of s is our closed loop transfer function. N of s is our numerator. As long as it's a polynomial, we don't care too much about what its form is. And then let's say our denominator in this case is a generic fourth order transfer function where a1, a0, a2, a3, etc. They're all just constants. And we have up to between s to the 0 all the way to s to the fourth. So if we're building a table, we need to have rows and columns, right? In a Routh table, the number of rows in the table equals the order of the denominator plus 1, right? You can label these rows as s to the n, where n is the order of our denominator, s to the n minus 1, all the way down to s1 and s0, right? So it's n plus 1 rows. In this case, it was fourth order. It's going to have 5 rows, right? The number of columns is take the number of rows plus, and divide it by 2, round it up, right? So n plus 1 divided by 2, round that number up. You don't normally need to label the columns, though sometimes you can in specific cases, right? So in this example, n is equal to 4. That means we're going to have 5 different rows here, and we're going to have 3 different columns here, right? 5 plus 1, that's 6 divided by 2. We end up with 3 in that specific case here, right? And so this is our example that we're going to be working with here, but this can apply to, s to the 11th, s to the 100 and something. It doesn't matter what our order is on the denominator here. It's appropriate for all different cases. So we need to fill out the entries of this table now. Let's start with that top row here, so s to the 4th here. What we're going to do is take each column to put in something for it. We start with s to the n, our highest order power, put that in the first entry. Then skip the next one, go to the one after that. So go to n minus 2, n minus 4, etc. So in this case, we would start out with our very first entry is s to the 4th. We put that coefficient in front where it should be a4 in that first point there. Then we skip A3, we go to A2. That's the second column in the first row. And then we skip A first, go to A0 here. So we're doing every other term, right? This is what we're doing. The columns, or rather the row labels, those are not just, we're not just going to write them straight down here. These represent actually different things, not just this polynomial directly here, right? So this is how we fill out our first row. With our second row, we're going to do the same exact thing, but we're going to start with n minus 1 instead. So n minus 1, that's 3 in this case, right? Because n is 4. So we're going to start out with a to the 3rd in that first column of that second row. Then we skip a to the 2nd, go a to the 1st. And then when we run out of things, right, there's no a to the negative 1 here. We just put in a 0 in that case. And that fills up our first 2 rows. So those ones are pretty straightforward. After that, we need to fill out the rest of the rows, right? So the remaining entries, we need to calculate a determinant using the previous entries, then taking the negative of it and normalizing it. Let's go through an example to see what that actually means here. So let's say that first entry there is B1. That's going to be the constant, and it's going to depend on everything that showed up above it. Let's actually highlight the stuff that's above it, just so we can kind of emphasize it. So we can see A4 and A3, the first column of the first two rows, that's going to be yellow. Then the second column is blue, third column is green here. For this description that we have here, B1 is the negative of the determinant of the yellow and the blue, right? We make it one big matrix, and then we're going to divide it by the entry that was directly, that was the first entry in the previous row, right? Which is A3 in this case. And that's how we calculate B1. A1, A2, A3, they're all constants. That means that B1 should end up being a constant here. Similarly, we can do this with B2 as well, right? But what we're going to do here, we're still going to use that first column, or the two rows in the first column above this one. But now we're going to move and use the green column as well here, right? So we're going to skip over it. So we're going to use yellow and green. So for every entry in this row, the yellow one is always going to be the first part of that matrix that we're taking a determinant of. And the second part is one to the right and the two rows above of whatever entry we're trying to do. And that's always going to be A3 on the bottom in this case here. For B3, we do the same exact procedure, but there's nothing to the right and above anymore, right? So that's all zeros is actually what's implying there. So we just put in zeros for that. So we have a pattern here. We can determine the values B1, B2, B3, and then repeat this process over and over again, right? So just like I said, no columns are left. So this is just a row or a column of zeros. So let's do it again. If we want to repeat this process to get the next row, so let's repeat it for, now we're going to highlight everything that's directly above this row. So now yellow is A3 and B1, blue is A1 and B2, green is 0 and B3. We want to get C1, C2, and C3 here. So C1 is the yellow stuff, the blue stuff, combine that into a matrix, take the determinant of it, get the negative, and then divide by the first entry in the row above. That's B1 in this case. And we can repeat that for C2 as well. We can repeat that for C3 as well here, right? So it's always going to be the same procedure here, no matter what you're doing in your Routh table. We can, again, do that for D1, D2, and D3, and end up with all of their values. Again, it's just the stuff directly in front of it or above it, right? It depends on the two rows that are coming above it. And so there's a pattern here that we can recognize. All right, so we end up filling out our Routh table, but our goal is stability at the end of the day, right? How does this actually help us determine stability, right? So we have a Routh table. This is a basic Routh table case, right? How can we determine stability? Well, we're going to go back to what we started with this section, the Routh-Hurwitz Criterion, and actually define it. So the Routh-Hurwitz Criterion says the number of roots in the polynomial, the denominator, that are in the right half plane is equal to the number of sign changes in the first column of the Routh table. Let's translate that into something a little bit more basic. If there are no sign changes in the first column, all our poles are in the left half plane, which means their real parts are negative and the system is stable. And that covers the Routh-Hurwitz criterion. The next video is going to cover an example for this.